An important message from Blue Ridge Hospice. There may be several hospices now claiming to serve the area, but Blue Ridge Hospice is the only local hospice that has been serving here for 40 plus years, operates the only hospice inpatient care center, conducts the only community-wide grief and bereavement programs, offers a nationally recognized music therapy program in conjunction with Shenandoah University, outscores every other Virginia hospice in Medicare's quality scores, and so much more. Blue Ridge Hospice, the first, the best. Find out more at blueridgehospice.org.
Earn great returns on your money with the safety and security of a community bank. Bank of Clark is offering 4.5% annual percentage yield on 6-month CDs, 4.75% APY on 12-month CDs and IRAs, and 5% APY on 15 and 18-month CDs. Plus, earn up to 3% APY on Bank of Clark money market accounts. Visit your local Bank of Clark branch today or go to bankofclark.bank. We're the bank for that. Member FDIC. Limited time offer. Rate subject to change at any time. Minimum balance of $1,000 on CDs. On MMAs, minimum of $1,000 to open, $25,000 to earn interest. Balance of $100,000 to obtain the 3%.
Check out the Your Financial Maven podcast, where we need to change the way we think about money, our understanding of it, and the effects. I'm Samantha Mittman-Besnoff, CPA, and I have spent over 25 years in the accounting field. The Your Financial Maven podcast will touch on things like saving and budgeting and really anything around money to help you feel financially empowered. Listen to the Your Financial Maven podcast on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.
Welcome, willkommen, bienvenido, bienvenue, benvenuti a tutti. Welcome, one and all. Thank you for joining me. I'm Dahlia Wilde, and this is the Oh My God Particle Show, where we talk about science and art and music and good vibrations and all matters near and far. So ready or not, unpack your imaginations and get ready to rumble through the universe that we are so lucky to live in. We are the stars.
Liability. Due to its heavy matter, this podcast could potentially warp the empty space surrounding it. At this time, no significant health hazards are known to be associated with this effect, except in Sacramento, Modesto, Tarzana, and on certain streets of the 90210 zip code. Should your head fall off, please do not consult iHeart.
Hi, I'm Dahlia Wilde. I'm the host of the Oh My God Particle Show. I love creating as much as I can. I just love art and science and where they meet. Thank you for being here. It's awesome to have you here. So here's the deal. Me and my dog Higgs Boson, we're on the way to CERN, right? But we have a really long layover in the UK. But it's awesome because this gives us a chance to drop into Oxford University to have a chat with some super geniuses who can explain a few things about the Big Bang and the birth of the universe. I have some amazing memories of Oxford when I studied there as a Truman Scholar. Okay, so I really want to give you guys the big picture of what we're dealing with here on the Oh My God Particle Show. So we got this gigantic universe of galaxies and planets and stars and rocks and particles, and then back all the way down to subatomic particles. So I'm going right to the source. We have Dr. Mark Kruse, who has guided me this whole time on my particle physics journey. He took me 1/3 of a mile underground into the Large Hadron Collider. Mark is a brilliant particle physicist, a kind, incredibly supportive teacher, and basically an all-around great guy who gets the spiritual and creative aspects of science and the universe. He's from New Zealand, teaches at Duke University in North Carolina, where I also went as an undergraduate, and he's a researcher at CERN. We'll be joined by Dr. Kruse Lintott, an astrophysicist at Oxford. He's a presenter of the BBC show The Sky at Night. If that's not enough for you, we also have Dr. Hannah Wakeford, an astrophysicist from Bristol University. She's a powerhouse investigating the atmospheres of transiting exoplanets using space-based telescopes. But wait, there's more! Chris and Hannah co-authored with Sir Brian May, the legendary guitarist of Queen, a very cool book called Bang, with 2 exclamation marks, Bang, the Complete History of the Universe. They're so enthusiastic and brilliant and especially inspiring. All 3 of these stellar guests are going to tell us more about the Big Bang, exoplanets, citizen science, particles. I mean, how cool is that? Art, science, music, all rolled up into one. See, it's all connected. This is a great conversation. I know you're going to love it. Okay, hit it, genius people. Hi, Hannah.
Hi.
Hi, Hannah. How you doing?
That's Mark Kruse from CERN and from Duke, and this is Hannah, the genius from Bristol.
Hi.
He was so helpful. I've asked him every dumb question and known to humankind, and he always answers it.
No dumb questions. There's no dumb questions.
No dumb questions. There's never a dumb question.
Thank you, Mark. We have Chris. Thanks for joining. You know Hannah.
Yes.
And Mark Kruse, genius from CERN and Duke
Hi,
and New
Chris.
Zealand.
How you doing?
It's kind of cool. I was thinking that how we're all in different places, and hopefully the people are interested in the world and the universe. So I'm like, I was going to say I'm the normal person here. I mean, I'm the lay person. Even though I went to Oxford, I was a biologist, and everything I've learned about particle physics was from Dr. Mark Kruse, who was kind enough. He took me a third of a mile underground into the Large Hadron Collider a few years ago before it was turned on. And Mark helped me cook up a theater show called the Oh My God Particle Show. And then this iHeart series is, based on those particle physics ideas. But I think my mission is to try to help make science cool and fun. And also that just men and women are all doing it together. It's no big deal. I mean, it is a huge deal what you do. But I just wanted to know more about the awesome things you're doing with citizen science, about your book, Bang, that you wrote with Sir Brian May now, and then just how you make it fun and make a living. Or I want to know about the Zooniverse, exoplanets, everything.
Cool. We should point out we're probably both quite sleep deprived. So the big deadline for proposals to use the new JWST space telescope is tomorrow. So every astronomer in the world is frazzled right now.
Oh,
Hannah more than most. So we should probably talk about that a bit as well, because I think that's deep.
We'll make a pitch for you. So, and what you could tell us what you want to do with the telescope, and how can we help you?
Yeah.
Because thank you so much for showing up and helping us. And because I feel like, I know you said the citizen science is a thing in the United States, but for some reason I didn't know about it, and I don't think most people know about it. So tell us whatever you want. Sleep deprived, just ramble on.
I'll let Chris take it first so I can collect my brain together from pieces across them.
Yeah, feel free. Tell us how amazing you are, but yet so approachable and cool, and how everybody should know about this. So.
In only 4 words, yeah. So I'm Chris Lintott. I usually describe myself as a distractible astronomer. So I started as a kid who looked up at the night sky and wondered what might be up there. And I've had the amazing fortune to spend my professional life looking up at the sky and wondering what might be up there. So I work on finding new ways to get information out of telescopes. I care about galaxies like our own Milky Way, but also distant galaxies in the early universe. But I have a sideline in trying to find planets, to find unusual things in the universe. And I've recently got distracted by rocks that come to our solar system from distant stars, what we call interstellar objects. And so I'm sort of interested in everything. But lots of the work that I do is done in collaboration with many millions of members of, well, hopefully your audience. So I run a project called the Zooniverse, which asks people to help sort through scientific data, through images of galaxies, through data that might reveal the presence of other planets, but also images of penguins in Antarctica, which need counting, and even some transcription projects looking through old historical records. And so that's fueled my sense of caring about everything, but it's also been a wonderful way to work. So we call this citizen science, and it's a big part of what I do.
So awesome.
Yeah, I'm Hannah Wakeford, and I really come from a planetary science background, and that means that I kind of started out studying the Earth, Venus, solar system planets, trying to look specifically at how the sun impacts our atmospheres and what that does to it. So I studied in the Arctic, looking at the aurora borealis, the northern lights, to try and understand the timelines from particles leaving the sun and then hitting our upper atmosphere and causing them to emit those beautiful lights. That really kind of took me on to just really loving atmospheres and everything to do with them. And I studied exoplanets and their atmospheres. They had only just really been discovered and started to be observed with telescopes like the Hubble Space Telescope. And we
have spent the last decade or so trying to understand what is in the atmospheres of alien planets. Hundreds of light years away, we can actually measure these worlds and what's in their atmospheres better than we can the ones in our solar system. So we're using now the brand new 6.5 meter JWST to get even more detail from these worlds, and we are constantly discovering brand new things. And I absolutely love atmospheres of all kinds, so I have huge biases towards various planets, and I just want to play with data. So primarily I'm what we call an observational astronomer. This means that I use instruments, telescopes, to measure the stars, measure different objects. And that produces for us, essentially, instead of those gorgeous pictures you see, we're actually collapsing all of that down into a squiggle. And that squiggle, the spectrum of the light, which is kind of the encoded fingerprint of what that object is made of, can really help us understand things about its formation and its evolution. So we're really interested in looking at the spectrum of all of these different molecules. And that actually takes us from these planetary atmospheres to the gas that formed them. So how did their star form from the disk? Where in the galaxy are they? What are these galaxies made of? How old are they? And that chemistry of that spectrum can take us all the way back through time. So it's all about taking those gorgeous images that we see and turning them into squiggles with error bars. And that's the bit that I really enjoy doing, is just really playing with it.
And Hannah's very, very good at this and is the world expert. So I should explain why we're both here, I suppose, if that's okay.
Feel free.
Yeah, something that happened to me, 20 years ago, nearly 15 years ago, was that I got involved in a BBC programme called The Sky at Night, which still exists. So The Sky at Night's been broadcasting since 1957. It predates the space age, so it started before Sputnik, the first satellite, was launched.
And I want to make it clear, it started before Kruse, so he's not that old.
Thanks, Hannah. Yeah, this is an old man role I think I'm playing here. But the Sky at Night used to be broadcast every new moon, because it was assumed that people who were interested in astronomy would want to look at the moon. And so if you do it when the moon's not visible in the sky, then they might watch television. The BBC lost track of the moon in the 90s. So now we're now a monthly show. But through this, I met the presenter who presented from 1957 all the way through to 2012 was Patrick Moore, who was a sort of English eccentric. He had a monocle. He talked very quickly and very seriously about all sorts of astronomical topics, but he was the authority on everything. And he'd become friends with Brian May, the guitarist from Queen. And they'd become friends because Brian May is an amateur astronomer. He made his first guitar with his dad in their workshop when he was a young boy. And they also made a telescope. But having had a major rock career and played Madison Square Garden and all the rest of it, Brian had some downtime, and so he wanted a new telescope. And I think if you're a rock star, you just go to advice in the right places. So Brian just called the most famous astronomer in the country and asked for advice on what telescope he should buy. So those two became friends, despite the fact that they shared no musical taste whatsoever. They're both very musical people, and there's no overlap in the middle. Patrick had the idea of getting Brian to write a book about astronomy because it would reach a wide audience. I happened to be in the meeting and both of them turned around and went, Chris should help write this as well. And so we wrote a book in the most ridiculous way possible, because Brian said, I'd love to write a book, but I don't have time. I said, I don't know how to write a book. I'm a PhD student. I've got other things to be doing. And Patrick said, don't worry about that, and wrote a book in a week and then sent it to both of us. And that's not the book that got published, because what then happened was we spent most of a year and a half sitting at Patrick's on the weekends, the three of us, going through the book line by line and working out how we could explain things. And the conceit of the book is that it tells the whole history of the universe in order. So we start with the Big Bang and we keep going to the far future. So, Earth forms about a third of the way through the book. Life appears somewhere in the middle, and then we have the future. So It's an interesting thing, and it was well received, and it's actually got out of date. And so Patrick's no longer with us, but Brian and I were talking, and we wanted to update the book. People were still buying it, and we felt that we needed to reflect all the amazing science that's happened in the last 15 years. And when we started thinking about that, what's interesting is that the science of the science of the grand scale of the universe, the science of cosmology, how did the Big Bang happen? What's the universe made of? What will happen to us in the end? Those things haven't changed in the last 20 years or so. But the bit in the middle, how do planets form? Are there planets out in the galaxy? How likely is it that an Earth-like planet will form? All of those things have changed dramatically because of the work by Hannah and her colleagues to find and understand these exoplanets, these planets around other stars. So I realized we needed somebody who was an expert in that middle section, the stuff involving rocks and atmospheres and that sort of stuff.
The fun things.
Yeah, the complicated things. See, to a physicist, the early universe is easy, right? It's when you start to worry about chemistry and atmospheres and all the rest of it that it's hard. And so I'd known Hannah for years and years. I'd interviewed her for The Sky at Night when she was a PhD student, talking about atmospheres on other planets. And so she was the perfect person to come in and talk. Sorry, that's Siri interrupting, if you heard that. She was the perfect person to come in and help us rethink this middle section.
And are you aging backwards, Hannah? You're so quite amazing. And I'm so happy to have you here, too, because we really want to encourage more women to get into STEM, but also that it's just natural to be extraordinary, So it becomes ordinary. And I love everyone just talking about science together, so it's not men and women separate scientists or serious about it. I love that you guys actually, have these great personalities and seem like we might want to hang out with you. Just like Mark. Mark, how does it fit in what you do, Mark, at CERN with what these two guys do?
Yeah, I think, both particle physicists and astrophysicists, we're asking the same questions, just in different ways. We're asking, what the universe is made of, how it's going to evolve, how did it start, and how are we even here to even ask those questions, right? And so, astrophysicists tend to, that they look out and make observations of the early universe. The further away you look, the earlier, the universe is that you're looking at, and so that they construct models of the universe by observations by looking out. In particle physics, we kind of do the opposite. We look in. We've got we build these huge and some almost like huge microscopes. Where we collide particles together with very high energies, like at the Large Hadron Collider, we're colliding, protons together with enormous energies. And in some sense, we're trying to recreate what the very early universe looked like. So when we do these collisions at the Large Hadron Collider, we're colliding particles with energies that naturally existed when the universe was about a trillionth of a second old. So in some sense, we're recreating the conditions of the universe when it had an age of about 1/trillionth of a second. So that means, we've been able to observe all the particles, that existed at that particular time. We've discovered the Higgs boson, for example. So now we understand that there was this Higgs field that permeated the entire universe around that time. And so, in some sense, we understand how the universe evolved from about a trillionth of a second onwards. The unfortunate thing is, there are a lot of really amazing things and without which we wouldn't even be here. But a lot of amazing things happened before that trillionth of a second. There was something called an inflationary period of the universe at about 10 to the minus 32 seconds, which is almost an indescribably small number, right? We can't get our heads around how small that is. But the universe expanded extremely rapidly at about 10 to the minus 32 seconds in this sort of what's called an inflationary epoch. We don't understand how or why that was initiated. And then we don't know, how or why the Big Bang even existed. We just label it as the Big Bang, the start of our universe. We've got no idea what exactly happened then. It's completely speculative. So all our theories about what happened a trillionth of a second and younger for the universe are purely speculative theories. There's some interesting ones out there, but I think we're probably a long, long way from really understanding that much.
So I like that we can take this in sequence. Yeah. So Mark, you do the first trillionth of a second.
Yeah, exactly.
Which we don't understand. Then I take over because I'm an observer. So I look out at the universe, and the oldest light that we can see comes from a period about 400,000 years into the history of the universe. So that's the point where we actually have evidence. We can infer some things about what life was like before that, or what the universe was like before that. But from 400,000 years onwards, that's my domain, and we think about how we got the structure we see around us, how galaxies formed, and really that's the epoch where it's gravity that matters, at least early on. Things we're now probing with the new telescope like JWST, gravity acts to sort of pull material together to form galaxies, to form clusters of galaxies. There's this grand dance that happens across the universe to form structure. But it's not too long, maybe. And we could argue about when the first planets are, but you get the first stars. The first stars are made out of almost completely hydrogen and helium. They produce carbon and oxygen and all the other elements that we know about. And so once the first stars are done, we then have the raw materials so that planets can form. And at that point, things get complicated. And so I hand over to Hannah.
Yeah, so taking over from that, that's when we enter the really big realm of the chemistry. How is the chemistry interacting? How are we forming materials that are combining those elements that are made in the stars together to create these more complex areas that we see in space? And that really starts out from these big, cold dust clouds where our stars and our planetary systems are forming, all the way down through that evolutionary period till we've got these fully formed planets orbiting around their stars and trying to understand whether or not there's a relationship between what's in the star and the environment around it and what's in the planet's atmosphere, how it formed, where it formed, and if it stayed there over time. So one of the really big things that we're learning by looking at these exoplanets, these planets beyond our solar system, is that the planets in our solar system didn't form where we see them today. They move around over time. Their orbits lengthen and shorten as they move closer and further from the sun. And that motion, that migration, as we call it, influences lots of different things within those systems. And we've seen from these exoplanets that there are planets as big as Jupiter, so 11 times the size of the Earth, 11 times the radius of our planet, 300 times its mass. But instead of being where Jupiter is, 5 times the distance from the sun as we are, these are 20 times closer, even closer than Mercury. They're on orbits of 4-5 days around their star. They're locked into this kind of dance where one side is permanently heated to thousands of degrees and the other is in permanent darkness. And it's all then about the dynamics and the chemistry of what's happening on those timescales. So we're going from the smallest particles and things that we really don't understand to the biggest things in our universe, galaxies, clusters of galaxies, all the way back down to looking at the atoms in these atmospheres.
Amazing. Why did they say that we're made of the stars? How did that all work out?
That's a Chris question.
Okay, yeah. So we have this. We actually had this. It was Brian Innovation. So we have this as the quote at the start of the first version of Bang. Joni Mitchell's quote that we're all stardust. So when the universe forms, Mark forms the universe, but he only manages, with his particle physics and his cosmology, he only manages to make a universe that contains 2 elements. It only contains hydrogen and helium. That's what the Big Bang leaves us with. To be fair, there's a sprinkling of lithium, but only the tiniest amount. And if you look around you right now, you're not going to see much hydrogen. You're not going to see much helium. And there's not even a sprinkling of lithium. Doesn't do much when you want, a kitchen and a table and some living beings to share the world with. And so those elements are all created in stars. So once you form stars are powered by nuclear fusion. They convert elements to heavier elements and release energy along the way. So our sun is essentially a machine for turning hydrogen into helium. Bigger stars, or stars nearer their ends of their lives sometimes, can turn helium into heavier elements. And so they produce the carbon, the oxygen, the nitrogen, the phosphorus, all the other elements, that the things around you that the Earth is made of. And so we think that the first generation of stars in the universe came quickly and burnt through their fuel very quickly and exploded in dramatic supernovae, which maybe one day we'll see. And those explosions spread material, heavier material, through the galaxy and enabled a formation of a second generation of star that could have planets made out of this extra stuff that we've created. Our sun, we know, is from looking at the pattern of elements that are contained within it and that we see in the solar system, we know our sun is a third generation star. So the stuff that you're made of has already been through 2 different generations of star to get to this point. And so, we are stardust in the sense that the atoms that make up our bodies have already existed in 2 stars. And it's really part of this story. I think one of the fun things about Bang was that we set out to tell the story in order, because stories are told in order. You have a beginning, a middle, and an end. So this seems sensible. But what happened was that the universe becomes more complex over time. More interesting things happen over time. I don't think I quite realised that. Mark and I can argue about it, but we could probably write down the equations that explain the first few seconds on the back of an envelope. And do a good job of describing the universe. You want to describe the atmosphere of the Earth or the way that planets form? We need computer code and a headache and at least a few years. And so Hannah's science is a science of complexity. I live in the middle of just looking at things, and Mark and the particle physics have a simple thing.
Yeah, it's quite remarkable that in particle physics, our goal really is to understand the fundamental nature of the universe, like the fundamental components, that what it's made of, the fundamental interactions, which then are used to make more complex structures. But that understanding will never be able to explain emergent behavior, like atmospheres and everything in some sense is just made of 2 things. I mean, fundamental quarks that make up protons and neutrons and electrons, and together they make up all the atoms. And so, where does all this emergent behavior come from, let alone, the emergence of consciousness? I mean, that still our brains are just made up of those 2 things, but somehow there's these other emergent sort of complex systems that exist. And it doesn't matter, I don't think it doesn't matter how well an understanding we have of fundamentally what the universe is made of. There's this big gap between different complexities that no theory can really bridge right now, and so it's really kind of fascinating. I mean, it's I don't think we've come to a crossroads yet, but it is a limitation of our models. Our models are really restricted in some sense, and I think explaining emergent behavior, complex behavior, is a real challenge. And right now we don't have a theory. Like atmospheres, we can't predict the weather. We don't have an equation that can predict the weather. We've got to run very sophisticated computer models. Does that mean that equations don't exist? Are we using even the right languages in order to form these equations? There's lots of open questions, I think.
Well, I like to say that when we were looking at that history of the universe and how our knowledge on it has changed over the last 15 years.
August 31st, Lil Baby presents It's Only Us Tour.
Made it out the treasure this type of
at Capital One Arena. Get ready for an epic summer. Lil Baby's IOU Tour has finally touched down. It's Lil Baby live in concert featuring the Kid LaRoy, Glorilla, Rilo, Rodrigo, and Honcho. Tickets are on sale now at Ticketmaster.com. Brought to you by Mammoth Live and AG Touring.
Our 20s are seen as this golden decade, our time to be carefree, fall in love, make mistakes, and decide what we want from our life. But what can psychology really teach us about this decade? I'm Gemma Spegg, the host of The Psychology of Your 20s. Each week, we take a deep dive into a unique aspect of our 20s, from career anxiety, mental health, heartbreak, money, friendships, and much more, to explore the science and the psychology behind our experiences. Incredible guests, fascinating topics, important science, and a bit of my own personal experience.
Audrey, I honestly have no idea what's going on with my life.
Join me as we explore what our 20s are really all about, from the good, the bad, and the ugly, and listen along as we uncover how everything is psychology, including our 20s. The Psychology of Your 20s, hosted by me, Gemma Spegg, now streaming on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.
The universe is 13.7 billion years old, but in the last 15 years we've rewritten 9 billion years of that in our knowledge that we've actually learned. You know, the whole middle section of Bang had to be completely reshuffled and understood, so where the complexity of forming our stars and forming our planets and understanding what that means and how they compare to other ones, that complex set of systems, what we can learn from our own planet through those models of things like the weather. So using these really grand models to make predictions. They make those predictions based on running millions and millions and millions of the same model with a different starting point and asking the question, how often does this one thing occur? What is the probability of it raining in this 10 kilometers squared in the next hour? And it's all about having the numbers and being able to run that to get an understanding of the statistical probability of an occurrence. And that's really where we're at when we're looking at these different places and we're looking across the universe. We're asking, what is the statistical probability of this being a representative of what we're looking at? Is this galaxy a good representation of all galaxies that look like this? Do all galaxies look like this? The answer is no. There's a whole range of different kind of types, and that's exactly the same for planets. There's a whole range of different kind of categories of planets, and we can keep dividing that down. There's whole ranges of different kinds of stars, and it's about understanding the relationship between all of those really complex systems.
And Chris, you had mentioned getting a headache, and I was wondering how do you conceive of this massiveness, right, without getting a headache? Or I know Mark and I had talked about that some particle physicists can get kind of upset when they get to the bottom and they find nothing's there. But it is also kind of strange to imagine such vastness.
It really is. I think there's a sort of sense of looking out into the universe that can boggle the mind. And I think it's very easy, as somebody who talks about astronomy in all sorts of audiences, it's something I can use very effectively. You know, I can tell you that, you know, the sun is just a star, that it's one of maybe a few 100 billion stars in the Milky Way galaxy, and that the Milky Way galaxy we now know is one of only a few 100 billion galaxies in the observable universe alone. And so what that means is that there are probably more stars in the observable universe than there are grains of sand on the Earth. And, you know, you can get people into this headspace where they feel awed by all of this. Now, there are a couple of things that I want to say about that. Firstly, we don't actually know how many grains of sand there are on the Earth. Turns out that's a much harder problem. So that's difficult, and geologists should work on that so that I can pin down my analogy.
I mean, that depends on what you call a grain. Where does something start becoming a grain?
Right.
When does it become gravel or a pebble? When does it become just an atom or a molecule? You've got to ask, what is that range?
But before we get distracted by that, I think, so that's the first thing. But I think the second thing is that I think when we do that, I think what I'm doing is giving the impression that I, as an astronomer, have some deeper understanding of what it means to be a being on a planet around a star that's one of a few 100 billion in a galaxy that's one of a few 100 billion. And I have no idea.
Yay.
We get used to saying the words, for sure. So I can say, you know, we are one of a... We're orbiting a star that's one of a few 100 billion, and not get distracted by it and ruin my Tuesday. But I don't actually have an understanding of what it is. But I think there is something about looking at the universe. If the universe is this vast, I think very seriously that as far as we know for now, we are the only beings in that universe that we know of that are capable of contemplating it. That are capable of looking up at the universe and trying to understand the behaviors of particles that Mark worries about, of thinking about whether there are other planets and even asking the question whether there are other beings like us out there. And I think there's something really important that therefore we do that. It may be that, next door there's an alien civilization that's way further ahead than we are, and then we can relax and goof off a bit. But for now, I think, we are the bit of the universe that thinks about itself. And that, I think, is the thing that gives not a headache, but makes me sort of stop for a second and think deep thoughts before I go back to my email or whatever else I'm doing.
It's exciting, though, that you mentioned that about all that uncertainty, but honestly saying that you might not know anything. But I was interested in that Vera Rubin. She said she got such pleasure from looking at things and trying to understand them. And
it's about understanding. I think it's about relaxing that you don't know. I think we do a bad job in both of our countries of teaching science as a set of received facts.
Exactly.
Not a process. I mean, Hannah, you were talking about being in the Arctic and trying to understand the atmosphere. That must be an exercise in realizing how much we don't know. I assume you've gone through your life without thinking about the fact that we don't understand the Earth's atmosphere, and suddenly you're there and confronting it.
Yeah, I mean, one of the hardest things that we do when we're teaching is get the students to realize it's okay that we don't know the answer to some things, that there isn't a definitive yes or no, or there isn't an equation that we can solve for absolutely every single process that we've got. Or if there is, sometimes it's not something that we can put in an exam for them. We can't solve that. You'll need a computer, I'm afraid. So getting the transition from understanding these principles, or even just being able to think about them and going, okay, but that can mean any one of these things, is a whole different way of looking at things. And it's a really hard thing to get around.
That's why I love where music and art and science, where it all connects, because that accessing that not knowing and really helps with learning, doesn't it? Because I went to a lot of great schools, and I still get so freaked out that there's one right answer, or, and I think it's really important to encourage people to, just to, explore. That's so exciting.
Yeah, I think encouraging failure is a good thing. I mean, failure is not a bad thing. And,
yes.
I teach both particle physics and astrophysics courses here at Duke. And, the first thing I say when I start is that, everything I'm going to teach you, especially in particle physics, and even in astrophysics, we're talking about the stars and the galaxies. Everything I'm going to teach you is just essentially 5% of the universe. In fact, we're teaching you all about observable matter, things that we're able to see and things that we're able to measure. But that's only 5% of our universe. I mean, so, there's 25% that's something we have no idea. It has some gravitational effect that we call dark matter. We call it dark matter because we have no clue what it is. We believe it is a form of matter, but we have no idea. And then there's a more mysterious sort of entity in the universe that's most of the universe, today. It's about 70% of the universe. We have no idea what that is. We call it dark energy because basically we have no idea what it is. It's presumably some kind of field, but it's having this anti-gravitational, anti-pressure effect on the universe, causing it to expand at an accelerating rate. So, so really we have absolutely no idea what 95% of the universe even is. And so, it's, that's our starting point.
So we should just have fun. So,
exactly.
And it would be cool to look at all this. And
sorry, carry on.
No, I know nothing. You carry on.
Well, I was just going to say, in astronomy, we have this other uncertainty as well, in that we don't get to go and reach in and manipulate what we're studying. So I would love to know more. We've got a neighbouring galaxy to the Milky Way called the Andromeda Galaxy, which we will, in about 4.5 billion years, collide with, but it'll be fine. Be safe. But I'd love to know more about Andromeda, but unfortunately it's a pancake and it's almost edge on to us. So we don't get a proper view of its disk. And the number of days where I wish we could just fly over and have a quick look down, that would solve a lot of my problem. But we can't do that. And Hannah, you can only see particular exoplanets, right?
Yeah, so we've just got these what we call transiting planets. These are planets that pass in front of their star from our point of view. So they have to be edge onto us. From us looking out from the Earth, that star has to be orbiting around, that planet has to be orbiting around its star in such a way that it blocks out some of that star's light. Only about 10% of existing planets will do this, will be at the perfect orientation. And it actually restricts us in terms of how far away we can look as well. We've discovered over 5,000 exoplanets, and they are all, in astronomy terms, right next door. They're really close by to us because it's so difficult for us to look even further away. But there are some methods where we can look directly at these planets, and that is, colourfully called direct imaging. Astronomy is a say what you see kind of subject. We are quite simple in that all of the things that we name things, they are based on just what they look like. So these directly imaged planets, we can get information straight from the planets themselves by blocking out the light from the stars. But that means that we're looking at these very different populations of worlds. Worlds that are passing in front of their stars are normally very, very close in. They have short orbital periods, very much unlike our solar system planets. And then we've got these direct imaging ones, which are really, really far away from their stars because we can see them separate from their stars. Again, very much unlike our solar system planets. So getting an understanding of where we come from and what our solar system, where it fits in this kind of grand galaxy filled with planets, more planets than stars, more stars than grains of sand. So imagine how many planets there are. And how can we really frame that? How can we piece all of these things together? And it's all about interpreting the invisible, interpreting these indirect measurements of what is there.
And Hannah, you can actually tell if a planet has an atmosphere in some of these methods?
Yeah, so when we're looking at these transiting planets, for example, as the planet passes in front of the star, some of that starlight shines through the planet's atmosphere before it reaches our telescopes. So we can pull apart that information. And if we look at the spectrum of the planet as it passes in front of the star, we can see changes in the amount of light being blocked. So if you've got something like water vapor in the atmosphere, water vapor likes to block light in the infrared. It's one of the reasons why our planet's nice and toasty. The Earth's atmosphere has a lot of water close to its surface that absorbs infrared light. It absorbs heat. So we can actually look for these fingerprints of water vapor in these planetary atmospheres by seeing how the planet appears to change size as a function of wavelength through its colors. So from that, we can build up all the fingerprints of different materials in the atmosphere. And not only can we measure what is there, but we can actually get an understanding of how much is there as well by looking at how much water there is compared to carbon dioxide or to methane or to sodium and these other materials in the atmosphere.
You guys are so fun. I feel like I want to come to all of your classes. And so I don't want to delay you with getting out those telescope proposals. Do you want to tell us a little bit about what you're going to be doing, and then feel free to escape. And I hope you'll come visit with us again, or we'll have to come to England.
Yeah, you should do the road trip. We'll show you some old observatories and some new data, which is always the fun thing of being a. So I think we said earlier that we're looking at putting in proposals to try and bid to use this new brilliant space telescope that we've got, the JWST, which is a NASA-led project, but it's also a European project and a Canadian one as well. So it's an international thing, and anyone in the world can ask for time. I think. I like talking about this stuff because I think people have the impression that scientists sit around waiting to have an idea, and then when we have a good idea, we go and do it. Actually, we have too many ideas, and so we don't actually know. This is the first proper big call for proposals, but the Hubble Space Telescope, which has been around for a while, gets 7 to 8 times as many proposals as can be carried out. And so we're all sitting here trying to write. Actually, Hannah and I are rivals, I suspect, because we want time on the telescope to do different
yeah, probably,
things.
Actually.
And so, I have a set of galaxies that have been found by volunteers on our Galaxy Zoo citizen science project. So people who've gone to galaxyzoo.org, classified galaxies, have found a particularly unusual set of galaxies where we think that the black hole at the centre of the galaxy has recently switched from a mode in which lots of material's falling down onto it. The black hole is feeding. That creates energy, and you get these jets of material that shoot out at nearly the speed of light. It's a very dramatic phase of a galaxy's evolution. And we used to think that there were galaxies that did this all the time with active black holes, and there were nice quiet galaxies like the Milky Way. And now we think that galaxies switch quickly between these two, and we're trying to prove that. And we need to take a closer look at the material that's being affected by the black hole. So that's the pitch. And we only need a little bit of time. They're quite bright galaxies.
All right.
And before Hannah takes over, and what we want are beautiful images. So none of this squiggle nonsense. We will get nice images of galaxies. Yeah.
Well, what I want is lots and lots of beautiful, exquisitely measured squiggles. And we've got there's a couple of theories that might sound absurd. Did you know that planets are three-dimensional? That is something that we actually haven't been able to deal with yet. Because of how complex these systems are, we have to collapse them down into this one-dimensional, okay, everything's the same everywhere. Because it's the only way that we can really bring all the physics, the chemistry, the dynamics together to make sense of it. But our models and our observations are much, much better than they previously were. So these new observations with the JWST, because it's a bigger telescope that can look over lots and lots of different wavelengths, and it's really, really precise in how it does that, we can actually measure the three-dimensional effects of the planetary atmospheres. So not only can we measure what it's made of, how much there is of those materials, but we can measure where in the planet's atmosphere those materials are. So we're proposing to use this nice new technique to try and spatially map where clouds are in the atmosphere, where the water vapor is in the atmosphere, and how as you go from these super heated day sides, which are hotter than a rocket taking off over the top of your head, to these really cool night sides, how does the transport of that material change what it's made of? How does the chemistry change as you go around the planet? So we're trying to take these distant one-dimensional squiggles and understand these full three-dimensional worlds and turn these exoplanets, these dips in the light from the star, into these real strange alien planets.
That's amazing.
Actually, Hannah, just a question. Is there anything from these atmospheric measurements that would indicate what kind of life there might be on the actual planet? Some more complex. Like for example, amino acids. I mean, I'm not sure they would get into the atmosphere, but is there some indication that you might...
So if we look at astrochemistry, we've actually found amino acids in star formation regions, in really, really cold clouds of gas and dust in our universe. Some of those most beautiful images you've seen from the Hubble Space Telescope, and now we're seeing from the JWST, in those images are amino acids. So we know they're out there in the universe. Measuring them in the atmospheres is a different thing, though. So one of the key goals of looking at some of these exoplanets is pushing to these smaller and smaller worlds. I said the ones we're looking at, these Jupiter-sized planets, but we can also look at things that are rocky. So rocky worlds, so densities similar to the Earth or to Venus or to Mars, and try and ask the question fundamentally, does that planet have an atmosphere? So before we can start looking for what it's made of, we need to ask the question, does it even have one? So the first thing we're doing with JWST is trying to detect these atmospheres. And then the next question is, what are those atmospheres made of? What does that tell us about the environment on the surface of these planets? What might the surface be made of? And how might that interact with the atmosphere to change what it's made of? So the Earth's atmosphere is not in what we call equilibrium. It's not balanced. And it's not balanced because we have volcanoes. We have an ocean which interacts with the atmosphere. We have life, which also interacts with the atmosphere. So looking for these different unbalanced materials that shouldn't exist together is a really key way of going. But the hardest question is asking, is that caused naturally, or does it fundamentally require the presence of life to exist? And that's a whole area of a science called astrobiology, trying to understand what is it unique about life that can change and modify an atmosphere that can't be created by any natural means.
You guys are mind-blowing. I'm gonna have to have a lie down. I want you to get those proposals out. So you are so awesome, all three of you. Thank you for being so inspiring and really showing that it's fun. Anyone can do science. We don't have to know anything. We just look into.
Just be curious.
Yeah, that's the main thing.
Yes, curious and fun. And you made my day. Thank you so much. I'm sure you inspired so many of our listeners too. And I'll make sure everyone sees your Zooniverse, your banguniverse.com. And what was the other one, Hannah? Stargate or something like that. I'll make sure I include them all. And CERN. And I hope we'll all be meeting up in person soon. So thank you for all your inspiration and really making it absolutely fun and cool.
That would be great. Can we plug 2 podcasts?
Plug away, please.
Podcasts. But so Hannah runs an amazing podcast called Exocast, which talks about the variety of planets and the fun that her and her colleagues are having. And I've got a new podcast in which I try and explain the night sky to my dog, which is Dog Stars Pod on Twitter and elsewhere. So I think your listeners would enjoy both of those, I'm sure, in their very different ways.
We would. I listened to it. Exactly. All right. Well, you guys are fantastic. So hopefully you'll get some sleep tonight and get those proposals out on time. And Mark, I will be discussing many more things with you and hopefully not giving you a headache. So have a great night and afternoon to you, Mark. Thank you for joining us.
Yeah, nice to talk to you. Take care, Dahlia. Talk to you soon.
Bye. Thank you. Wow, that was so inspiring. I mean, my mind is blown. We got universes, galaxies, stars, planets, exoplanets, rocks, pebbles, grains of sand, particles, subatomic particles. I mean, it's so much to dream about. Thank you for being part of the OMGPS Club. It's a pleasure to have you here. Make sure to check out Chris and Hannah's book, Bang, co-written with Sir Brian May, banguniverse.com, and watch Chris on the great BBC show, The Sky at Night. Remember, keep looking up, stay positively charged. We are the stars. Goodbye for now. Adios. Arrivederci. Auf Wiedersehen. A biento. Join us next week on the Oh My God Particle Show for more adventures with mind-blowing creative scientists and awe-inspiring scientific artists. We've got 2 geniuses from the Large Hadron Collider at the Center for Research Nuclear in Geneva, Switzerland. It's gonna be a blast.
Note, this podcast may actually be 9-dimensional or more, but if this is the case, to the best of our knowledge, vibrational functionality should not be affected by the extra 6 or more dimensions. As required by our legal department, no money-back guarantee exists that covers additional dimensions and their as yet unknown quantities and realities.
The Oh My God Particle Show is part of Seneca Women Podcast Network and is produced by Dahlia Wilde and iHeartRadio with sound design by Paul Mercier.
Check out the Your Financial Maven podcast, where we need to change the way we think about money, our understanding of it, and the effects. I'm Samantha Mittman-Besnoff, CPA, and I have spent over 25 years in the accounting field. The Your Financial Maven podcast will touch on things like saving and budgeting and really anything around money to help you feel financially empowered. Listen to the Your Financial Maven podcast on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.